welcome back, everybody. And right now, it's my pleasure to introduce Professor Martin Jaggi from EPFL. Martin is a tenure-track professor. He's heading the Machine Learning and Optimization Lab at EPFL. Before that, he was a postdoc at ETH Zurich and the Simons Institute at Berkeley, and also EPFL. He earned his PhD in Machine Learning and Optimization from ETH Zurich in 2011, and also a master's in mathematics from ETH Zurich. He's also a fellow of ELIAS and a co-founder of EPFL's Applied Machine Learning Days. We're so excited to have him with us. So Martin, the floor is yours.
Cool, thank you so much. It's great to be here. Thanks so much for organizing this. I hope I can see the slides. Looks good. Yeah, so I'd like to talk a bit about federated learning with gradient-based methods. And so the standard setup applies. Our goal for the moment would just be to train a model collaboratively, that several data providers together train a model, which hopefully is going to be as good as possible, maybe as good as the centralized comparison setting if all the data would be put into one place, as illustrated on the top right. How we collaborate in this is going to be varying a bit depending on the application, and I would like to discuss several use cases in the next few minutes. All of the methods will be based on standard gradient descent, or more precisely stochastic gradient descent, that we pick small mini batches on each worker. We send usually a gradient or a pseudo gradient to the cloud when we participate, which you see on the right, for example. And that's the basic building block. But to make this a bit more precise, I want to address like 3 scenarios here when the gradients are not necessarily the usual unbiased estimators, which they usually are. And the first use case for this is when I want to discuss this in the federated learning setting when we have client drift. So this, I guess several of you have heard already, of course, when there is heterogeneous data, when every client has a different data distribution from the others, then federated learning can be more challenging. And why is that? I think the main reason for that is really this problem of client drift, which happens when we do more than a single iteration on every gradient and on every client. We do gradient steps on the local data, as you can see. For example, the evolution between one communication round, which is illustrated on the bottom right, which we perform like 4 local SGD steps on this worker, illustrated with the blue points. And the problem we have is that if you continue this for many steps, then you will converge to the optimizer of the objective function from that client. But of course, the minimizer of that client has nothing to do with the minimizer of the global problem necessarily. So what we have to do is we're not interested in converging to the set of all these local minimas of the individual clients, but we are interested into converging to the optimizer of the global problem, which is the sum or the average of all the objectives. So that's the goal, and that's also the problem that we face when we have several local iterations. To formalize this a bit more, so we will use yi for the local steps between the communication rounds. After a number of local steps, we aggregate again, very standard, so standard federated averaging. We average by communicating the average of the models after the communication round. Then, how are we going to cope with this? So, I want to discuss one way to deal with this, which is called Mime, which is a mimicking centralized optimizers. So we're going to get to that why it's called like this. So the problem is a bit that, as we have said, that we converge to different optimizers, which we, for example, have illustrated on the left here, and on the middle you have the optimizer of the first objective might be x1 star, and the optimizer of the second objective might be the green point x2 star. And they have nothing to do with the true minimizer, which is the orange point. And now you see what will happen in federated averaging, as we already said, is that they show client drift. And then after the communication round, this might be compensated a little bit by applying momentum. And the momentum vector is illustrated in all these pictures in red. It's showing that after we have done these local steps, we apply servo momentum. So the server receives that, computes the average, and then we'll actually add this momentum, which is resulting from the pseudo gradient from the entire round to speed up the optimization process. So we know from centralized methods that momentum can help to speed up optimization. However, here we see that does not really solve the problem of client drift. Now, the idea how to improve this is really simple. That we compute the same kind of momentum on the server after the communication round. So we compute that globally after each round, but we do apply it locally as well. So that's the novelty here, that the momentum vector, which is the red one, is not only applied after the round, but it's applied in every local step internally. So you do a large number of local steps if you want to save a lot of communication. And within each of these steps, you will apply a little bit of this global momentum vector which you got from the round, right? Within all these local steps, the momentum vector is constant. It's only going to change in the next iteration. And from the picture, you can already see that if you do this, you have a much less severe effect of client drift because this kind of drift is compensated in every step by the momentum, making it much less severe, making them converge more closely to the true optimizer, which is the global optimizer, here illustrated in orange. Now, of course, you might not believe me, that's just an intuition. So can we actually prove something like this, that momentum might probably help? And this is hard because it's also not completely obvious in the centralized case. That momentum has several effects. It's kind of much easier to analyze in the deterministic case. In the stochastic case, it's much harder. But what I also wanted to say here is that the motivation here is not only to get a speed up, like you would do in a classic setting, but the motivation here is also that we want to reduce the drift, right? So we actually might even use stronger momentum here than just from an optimization perspective to actually counteract the drift. The general theme of all the applications I want to discuss in this talk is a bit this, that the gradients we get here, they might not be what we usually expect, right? So we want to kind of have a reference point or reference direction to correct them and to transform them into a gradient which actually helps our goal. And here we can see that the central servo momentum is going to play that role. That's the red vector, which is going to help us to transform these blue gradients and make them actually useful for the actual task. So that's the spirit here, and this is the first example of this theme I want to discuss. In terms of theory, this is just a formal definition of the algorithm. It's exactly what we said. We will use a local step y. It's just using the standard gradient computed on my local data, and it's going to use the momentum vector, as we said, is going to be added locally in every local step. And then after the communication, it's going to be aggregated on the server. And there is an additional communication step happening here, actually, that we also will aggregate gradients, fresh gradients at this reference point after the communication. And we're going to update the server, we want to update the momentum only on the server. So this is the second line on the slide here. In terms of convergence, the picture looks a bit like this, so don't be too scared. So what we have so far is that what's already used before is a scaffold, which is an algorithm which has a bit of similar spirit. The idea in scaffold is a bit similar, that you actually try to learn the difference of these blue biased gradients you have. You're trying to learn the difference of those to the gradient you want, which would be an unbiased one. So this idea of learning this difference is also called this control variance, right? If you just learn the difference vector. So, but learning this takes a lot of time. It will take each client if you want to learn the difference vector of that client to the global direction, it will take you a lot of iterations. That client needs to appear many times until you have a reliable estimator of this difference. This is much improved in Mime, where we do not have any dependency on the number of participating clients n. So here we can really, this is the first time that we can actually get a rate comparable to the centralized training, which we also have on the very bottom. That's if the server would train alone, everything centralized, then we would have the rate on the bottom, which is basically L over epsilon to the 3/2. That's the main leading term. And I should also explain what zeta is here. Zeta is the variance we have between the different clients, so the data heterogeneity. This is measured just as the variance between the participating clients. And then sigma, as usual, is the variance within one client. So the standard kind of noise term that you have in SGD. There is one more term which you might find confusing here, and that's if you look at the green algorithms here, they depend on this strange quantity delta. And delta here is the variance between the clients in terms of the Hessian. So the Hessians might be the same. So this is the domestic quantity for each client, but they might be different on each client. So we use this as another measure of data heterogeneity. How different are these objectives between the clients? Do they have their optimizers in a similar range? So that's measured by the Hessian dissimilarity. And we don't need to be scared of delta because delta is always smaller than L, the smoothness constant. So what's happening here is that these rates are matching the lower bound. Even better, they're actually beating the lower bounds. The green convergence rates from the Mime variants are actually strictly better than the lower bound. How is that possible? I need to be more precise. So the lower bound is in terms of number of gradients we do on the server, but the trick is that the green algorithms are in terms of number of communication rounds, which we do here. And of course, when you have these federated algorithms, they can perform several local steps within such a communication round. And this is allowed here, and that's why we can get strictly better convergence here. And the convergence is strictly better if and only if the delta here is smaller than the L. So, I mean, this is always, they can be equal, but if the Hessian dissimilarity is even better, then we get a strictly better upper bound here, kind of beating the lower bound, which is a nice property. I didn't explain all the details of the Mime algorithm, which is using the variance reduction technique from the momentum-based variance reduction. But the light version of that has the advantage that it doesn't need any additional memory and doesn't need any state here. And also in its scaffold, you will have one more vector which you need to learn for every client here, which we do not have in those variants here, because you just use the simple global momentum in which you apply in the Mime light variant. But the theory is better for the full Mime variant, which is a bit more complicated. Yeah, that was a bit short overview, but I want to move further for the second application, which you're going to consider, where we have kind of strange or unusual gradients. And that's when we move to personalization. So everything so far was federated in the default setting. But now when we try to push a bit further to the more user-centric model, where every user can decide on their own who they want to talk to, and maybe we have a decentralized scheme, also a decentralized communication graph, potentially. And every user has their own objectives that they might want to learn a different model than the other users. So that's called the personalized setting in collaborative learning. To be more formal, what we've done so far was federated with every client contributing to the global model. So want to learn the model on all the data. But now we want to learn models on the individual data. Every user has their own objective function fi and their own training data for that. And the question is, the gradients from other users, which correspond to different tasks, could they still be helpful for us if we speak from a perspective of user 0? So user one might learn a completely different problem, have very different gradients. I mean, for example, if their labels are flipped, it might be very difficult to understand that I can use their gradients as well, but I need to flip them around to make them useful for my purpose, which is to use the optimization function F0, or to make progress on F0. How can we do this? So what we have here is a very simple setting. So these are two algorithm variants. One of them, the first one, is just using a very simple scalar weight to kind of learn who is useful for a particular user of zero from that perspective. So F0 gets all the gradients from these collaborators, but these are friendly collaborators. They do send us their gradients. Also, they are even nice enough to send us gradients which are computed on the same X. So this is not about the consensus problem, but this assumes that I, as user zero, I send out my X, and everyone will be friendly enough to compute a gradient on that particular model, but on their data and on their task. So they have potentially very different labels and very different FI functions. They send back their gradients, and I, as user F0, have to decide how do I want to weigh those to make them most useful for my objective F0. Slightly, you can imagine that this is a bit limited, so because we don't have much flexibility. There is one version which is going a bit further than that, which we have on the second line on the slide. And that version is really a bit the same idea as we discussed before. We had we mentioned a scaffold that we had in federated setting. We had this global kind of vector which we tried to mimic, and we tried to learn a difference vector from these candidates we got to the ideal unbiased gradient. And this is a bit similar here. We try to learn a vector C, which is describing how that particular collaborator Fi, how is that collaborator different from my objective, what I really want to get. I want to get an unbiased gradient for F0. So I'm learning the C vector, trying to get progress on my own objective. And this can actually be analyzed as well. And again, the assumptions we have to put to make this theory work are a bit similar than the ones we saw in Mime. But what we're most interested in this personalization setting is the speed up we could potentially get from our collaborators, right? So the question is really that if I do this collaboratively, do I gain in the sense that am I going to be faster than training alone? So this is the question, because I can just train alone on my data available on my node, where I have the variance sigma squared, and F0 is the initial error. So if I train alone, I would just get the standard rate, usually smoothness times this, with scaling with square root of the number of steps. So this would if I would train alone. But now in this setting, we see that we do get actually a linear speed up when we have n collaborators who help us. And this requires that we do a very large number of steps. So it's, of course, it's not a global convergence guarantee. This is just saying that the gradients are going to become small on our objective. Requires a large number of steps, requires same assumptions as we had before, that we do actually, this is influenced by the dissimilarity between the tasks as well, which I do not show here in the O notation, because the dissimilarity of tasks is mainly going into how do we select these collaboration weights alpha. But if we select them correctly, according to the dissimilarity of gradients between tasks, then this rate holds here, and you also have to set the step size accordingly, and then this rate is going to work. And again, showing the linear speed up, which is nice here. So how is this related to the overall team again? Again, it's similar that here we actually also do use a special kind of learning item to learn this reference vector CI. So trying to capture how this collaborator is different from what we want it to be. Trying to learn that, and the learning here is extremely simple. It's a bit similar to the momentum idea we had before. Here we just use exponential moving average from whenever we get a new gradient from that collaborator, we do add it to our exponential moving average. That's that's this part. And again, the assumption is similar to that before. And we also can see that the bounded Hessian dissimilarity is also assumed here, but it's implied again by smoothness, and it's only going to influence the step size and collaboration weights. All right. So the last application I want to discuss is quite different, but again, the same high-level idea is going to help us to attack this thing, but attack actually is the wrong expression, because we would really like to defend ourselves against collaborators which are trying to game the system and trying to break the collaborative learning. So this is the so-called Byzantine robust training setting. So we might have a subset of the clients which are trying to act maliciously, or which is faulty, not reliable. So this is the setting, and the question is, can we use similar ideas again to trying to learn if a collaborator is actually useful or is a good collaborator, or is one who's trying to break the system and give wrong gradients to lead the conversion somewhere else. So that's what we said already. Basically, some clients might be the good collaborators, some might be malicious, sending arbitrary messages. So there's really no restriction. The malicious clients can be omniscient, they know everything that's going on. They might collude with each other, and they just will send something which looks like a gradient to us. We can see this from the server perspective. We don't know anything about it, we just get this kind of vector which they claim is a gradient. Then there's of course unstable clients which might also send like wrong information, or maybe they might send nothing, which could be interpreted as a vector of all zeros if they're just not present. So there's another way that we get wrong gradients, so to say. Can we deal with that? Can we achieve that the server still converts to the correct global model? And by global model, I mean the model which would result from only the good collaborators participating. Making this a little bit more formal is again, so just use federated averaging. That's what you would usually do if you average. But then, of course, you do not get robustness, because the mean is not a robust statistical estimator. So, of course, just one bad actor could arbitrarily influence the average and break conversions of federated averaging. So people use other robust estimators instead of these gradients which are sent by these users, some of them good, some of them bad. One of them is called the coordinate-wise median. Others, the earliest one was maybe the crumb estimator, and there's plenty of other estimators which take gradient candidates and then trying to do something like a median to result again a vector which hopefully is more close to what you would get if you would only average the good collaborators. So is this enough? Can we just aggregate these gradients and then it's going to work? This is actually not possible. There was a paper which was called Fall of Umpires. That's the white slides like this. And what they used there is that the problem is that attacks can be coupled over time. This was not addressed in previous methods. They only were thinking of gradient aggregation rules as being stateless. So maybe it's going to be okay for one round, but the problem is that you do 1 million rounds, so and then over each aggregation step, a very small error might happen, and the attackers, of course, could couple their attacks over time to systematically bias the whole training through the long conversions time. So this can actually be formulated more strongly. You can show that actually no aggregation rule can work if it's not going to use history. So these rules which were existing so far to aggregate gradient candidates, most of them did not use state, and then as from this result here, you would see that they cannot succeed in training. So we need to use state. We need to use history. We need to have some kind of memory to over time learn if workers are good or bad. And again, the problem should remind us of all the three themes we we're discussing here, it's always the same, that we have a candidate of a gradient. How do we make it useful for us? We need to compare it to something we trust, to have a good reference kind of vector. And that's, again, we're going to just use simple momentum. And in this case, it actually will be the worker momentum of each participant. And you can imagine that that vector is going to be much more stable to then be aggregated. Because in this coupling over time, the problem is that there's so much noise in SGD that if you see these very noisy gradients, it's impossible for you to tell if this is having a very small epsilon bias dragging you in the wrong direction. But if you do momentum, so here the momentum is not for an optimization purpose. It's really just for the stabilization purpose to remove the noise so that you can better detect if a collaborator is good or bad. So you might actually use much stronger momentum here than you use in a pure central optimization technique usually. So because it serves a different purpose here to detect who is a good and a bad collaborator. So after we have received this momentum stabilized gradient estimate, so here you can think of G being the stabilized one, then we still need to decide is this now a good or a bad collaborator? And the way we do this is by clipping. So we just clip the gradient compared to a center and the clipping radius tau, so that of course the big outliers are removed and the clipping radius can be carefully chosen such that you can get the optimization guarantee. The center is also a discussion, what is going to be a good center. We can prove that if you use the previous aggregated server state, so previous model on the server, you can use that as a clipping center and to get a convergence guarantee. It is kind of the first theoretically justified convergence result when you really get convergence to the true optimum of the good guys or good collaborators with this standard assumption optimization. For this, we also need to assume that we have such a robust aggregation rule, which is, for example, the case for the clipping rule I just showed you on the slide before. So we do recover the usual kind of SGD result you have for good workers only, except there is a small slowdown here, which is by delta, which is the fraction of the bad collaborators in the system. And that's all of it. So I'm trying to summarize the three directions we had. These are the paper links. And we also try to take some of these ideas and implement them in code. And we do this actually in a JavaScript library. If some of you might be interested, I'd be very happy to chat. We're using TensorFlow.js to implement some of these methods in the federated case and also in the decentralized case. And thank you very much. Happy to take some questions.
Thanks a lot, Martin, for this really nice talk. We are actually running a little over, but I think we can take maybe one or two quick questions. So anybody has a question for Martin? Jung, do you want to unmute to ask your question?
Yeah, I have a question about the robust aggregators. You mentioned that can be used for Byzantine like this robustness. And the technique seems to involve clipping and all that. I think what we usually do, like in differential privacy, is we do client level clipping. Instead of clipping after aggregation, we clip before aggregation for every single updates. And then we apply, we also can apply momentum to that. Then it's like clipping, aggregation, then momentum. A little bit different from what you did for like how you do momentum and the clipping. Do you can you comment on how this may affect the robustness? Thank you.
Yeah, so actually it's the same here that the clipping is applied on the client, so client side, and here the momentum is client momentum. So that's different. It's different from the very first part in the talk where we used server momentum. So here we use client momentum and client side clipping. I'm not aware of the DP results that you mentioned. It's very interesting. So I have not looked at the differential privacy connection, and it would be very interesting to consider. Thank you.
Thank you.
We can take another quick question if there is any. Zach, do you want to ask your question?
This is not a quick question, but I was curious if you had thought about kind of when to decide on using something like Mime versus using the personalized learning. I mean, there should probably be some kind of threshold at which you decide to use one or the other. I'm just curious if this is like too hard a problem to solve, or is this something that you've thought about?
To be honest, for personalization or not, I don't know. I'm not sure when personalization might be necessary. So it's I guess for use it's also maybe you could use these vectors here, which you get from Mime and also from the personalization technique, where we learn the differences between workers. Maybe those could be used to actually also decide if a global model is good enough for me as a user, or if I want to switch to a personalized model. What might also make sense is that maybe you only have some layers of the neural net to be personalized and some of them to be global. That also makes it a bit easier. Because if you have very little data, it's very hard to fully personalize a model. So there might be a middle ground there. Thanks for the question.
All right. Thanks a lot. We're actually over time, so if you have questions for Martin, please feel free to drop them in the chat box and he can directly answer you there.